called ordinary double point singularity, which is absolutely fascinating. And we talked about the fact that you have, what did I say? So I started with C3 acting on C4 with weights 1, 1, minus 1, minus 1. And then I said there's two different quotients you can build, because you can either cut out the locus where the first two coordinates don't go to 0 and quotient that guy, or instead you can cut out the locus where the second two coordinates don't go to 0. So you have two different choices of what quotient you're going to take, and they give you genuinely different spaces. In this example, they happen to be isomorphic, but I tried to convince you should ignore that fact and think that this is really something you can do to a space. This is a birational transformation, which turns one space into another. And then we use this idea of windows to show that although the spaces are being changed, the derived categories actually haven't. So you get a derived equivalence, two spaces with the same derived category. And the way that we did it is we considered this window, which was generated just by two line bundles in the equivariant derived category of C4. And then you have these restriction functors to both sides. You take an equivariant sheaf on C4, you can restrict and get a sheaf there, or you can get a sheaf there. And the point is that if you just restrict yourself to this subcategory, then it's equivalent to both sides. And so the two spaces are derived equivalent. Right? That was what we did on Tuesday. What I want to do today is, what I want to do is probably more than I am going to do. What I want to do today is talk about some other examples where some slightly more interesting stuff happens on the level of categories, and yeah, then get into this examples that involve orbifolds that have a lot of overlap with what Nick was saying. So I'll just rehash some things Nick said, but you can probably handle that. OK, but the first thing won't have any orbifolds in it. I just want to do that example again, but with slightly more general numbers in it. So let me let C star act on C to the n plus k. So I've got a first set of variables and a second set of variables. And on the first variables, you're just going to act with weight 1. And on the second variables, you're going to act with weight minus 1. Right? So I've got x's and y's, but now I'm allowed different numbers of them. N of n x's and n y's. Right? So this is x1 up to xn, and y1 up to yk. And it just for sort of simplicity of speaking, let me say that n is bigger than k. Right? It doesn't matter. I just don't want to have to keep changing the options. So again, there are two different quotient spaces you could form, right, in exactly the same way. So you can form x plus, which is the locus where the x variables don't simultaneously vanish, and quotient that by C star. And what does that look like? Well, this is something we now have a bit of practice in. It lives over projective space in the x variables, right? If you forget the y's, you get down into projective n-1 space. And the fibers are vector spaces of rank k. It's a rank k vector bundle over projective space. And which one is it? It's O minus 1 direct sum with itself k times. And that's living over Pn minus 1, where the Pn minus 1 is with x coordinates. Right? And then similarly, you can form x minus, which is the locus where the y guys don't go to 0, quotient by C star. And what's that? It's the total space of O minus 1 to the n over Pk minus 1 in the y variables. OK? And now we want to play our windows game again. Right? But again, we've practiced at this now. I don't need to rehash all the proofs. All the proofs are exactly the same. I can construct subcategories in the equivariant derived category which are equivalent either to x plus or x minus, and all I have to do is choose the right number of line bundles to sit in them, right? And then all the proofs will just go through the same as they did before. So if you care about the space x plus, then you say, well, x plus is living over projective space of dimension n minus 1. So we know how many line bundles we need. We need O up to n minus 1, because that's what Bailynson's theorem tells us. So let me have a first window which consists of the line bundles O up to O n minus 1. That sits inside the equivariant derived category Cn plus k. And then I have this restriction functor restricting to x plus, and it will give me an equivalence between W and the derived category of x plus. Right? Just as what happened for the Atiyah flop, just with some different numbers in there. On the other hand, I could care about x minus. So let me have a second window, win W prime, which is going to be O up to O k minus 1. Again, in the equivariant derived category. And that guy is tailored to be equivalent to x minus. So if you look at restricting to x minus, you get an equivalence. OK? Now, the situation is no longer completely symmetric. In the Atiyah flop case, that's the case n and k are both equal to 2. We just said, well, the same window is equivalent to both sides. Right? Well, here we have to just be, infinitesimally more observant and say, OK, these are different windows, but at least one of them sits inside the other. So this window prime is just obviously a subcategory inside W. Right? Just because it is. It sits inside it. So what does that tell you? It tells you that this category, derived category of x minus, sits inside the derived category of x plus. Right? This statement is stupid. That statement is not so stupid, not so obvious. So what do we get? We get an embedding, not an equivalence, but an embedding from the derived category of x minus into the derived category of x plus. So you can think of the derived category of x minus, if you like, through this construction as a subcategory inside the derived category of the other space. Now, certainly in Sasha's talks, you've heard a lot about admissible subcategories, right? And that's something that's quite important. And indeed, this is an admissible subcategory. So to see that it's admissible, you have to write down the adjoint functor. And here, that's not so difficult, because if you think about it, you already have a functor which goes the other way. Okay? So we have a functor which goes from the bigger category, the derived category of x plus, use the fact that it's equivalent to the big window, W, and now from W, I can just restrict down to x minus. Right? Now, that's not an equivalence. It's an equivalence on W prime. It's not an equivalence on W, but so what? It is still a functor, right? So I have this functor restricting from W down to dB of x minus. Right? So I have a functor that goes from there to there by using the bigger window. And exercise, that thing is the adjoint to the thing on the upper board. Okay? And if you're really, really on it, you can figure out whether it's the left adjoint and the right adjoint, which took me about 15 minutes yesterday. The exercise tells you which adjoint you're supposed to be doing. And I probably got it right, 50-50. OK, so if the functors are adjoint, then that tells you it's an admissible subcategory, right? The inclusion functor has an adjoint. And an admissible subcategory is the same thing as a semi-orthogonal decomposition. Right? If you look at the kernel of the projection functor, you discover the other half of the semi-orthogonal decomposition. This thing fits which way around? Doesn't really matter. You can do it in the exercise on today's sheet. You can go through and figure out the left adjoint and the right adjoint and the left orthogonal and the right orthogonal. It's all much of the same. OK, so this is a situation where the derived category of a space has a semi-orthogonal decomposition, and one of the pieces is actually the derived category of another space. Right? It's not just like when you have an exceptional collection and, OK, it's the derived category of a point or something, but this is maybe an interesting category. This leftover category, it turns out, is something that's not very complicated at all. This is essentially something that has an exceptional collection. Right? So in some sense, all of the interesting bit of this category is concentrated here. And the thing that's here is actually the derived category of another space, a different geometric object. So it's kind of fun, right? And it's not very difficult, right? We've just proved it with the windows very quickly. It's not the only way to prove it. There are other ways to do it. So let me just mutter some words about the geometry of this situation. So what have we got here is a birational transformation, right? Like the Atiyah flop, but more general, between x plus and x minus. Right? They're birational. They're isomorphic away from a thing of high codimension. And this kind of birational transformation has a name. It's called a flip. The special case when n and k are the same is called a flop. Like the Atiyah flop. This is a kind of pretty weak joke about flip-flops, by the way, which is not mine. It's due to Miles Reed, like most weak jokes in mathematics. Right? And some good jokes as well, to be fair. So these things are called flips and flops, and they're like, example 0 of birational transformations. Right? The minimal model program, considers these things beneath contempt. I mean, this is baby birational geometry. But it's the good place to start studying derived categories. And again, yeah, something I stressed with the Atiyah flop is that you should think of this example as a local model. Really, you should think that you have some bigger space, which you don't necessarily know much about. But inside it, maybe it has the projective space, a copy of Pn minus 1. And the normal bundle to the projective space is O minus 1 to the k. Right? And then locally, you do this procedure. You take out the Pn minus 1, and you put in a Pk minus 1, and you leave the rest of the space alone. So what we've written down is a local model for something that can actually be done globally. And the derived equivalence, when you set it up right with a little bit more care and attention, you can get the derived equivalence to work globally as well. So whenever you have two spaces that are related by a birational transformation with this local model, then they are derived equivalent. Right? Just by upgrading the kind of ideas that we've used. Yeah, and I should make a comment about the canonical bundle. So let me just tell you, if you want to know what the canonical bundle of the space, for example, X plus is, the way you do it is you take the contribution from the base space, which is O minus n. That's the canonical bundle of Pn minus 1. And then you get another contribution from the fiber directions. They contribute the determinant of the dual vector bundle. Right, this is just a fact about the canonical bundle of the total space of a vector bundle. This is what it looks like. Right? So the answer is OK minus n. On the other hand, if I computed the canonical bundle of x minus, then the numbers would go the other way, and I'd get ON minus k. So this is negative, and this is positive. So in some sense, kx plus is smaller than kx minus. Right, we're going through a birational transformation, and we're increasing the canonical divisor. Right, in some sense that I'm not certain I could make precise if you forced me, but some people could. And so the embedding of the derived categories is going from the thing which has a bigger canonical divisor into the thing which has a smaller canonical divisor. Right, things which have a very negative canonical divisor, something like a Fano, you expect the derived category to be big and have some boring pieces you can throw away and then have a leftover piece. If you take the canonical bundle to be very positive, so it's general type, then you don't expect to be able to do that, but it's possible that you can sit inside a bigger category in the way that we've done here. All of that is probably hopelessly vague. There's one special case that's worth pointing out because it involves famous words, which is the case right in the middle when n equals k. That's the case that both of these canonical bundles are trivial, which is what Calabi-Yau means. So x plus and x minus are Calabi-Yau. The canonical bundles are trivial. And that is exactly the case where you get a derived equivalence. Right? When W and W prime are the same thing, and the categories are the same thing. Yeah, and again, it's true. When n equals k, both sides are isomorphic, like they were in the Atiyah flop, but ignore it. It's not important. Forget that they're isomorphic. The point is that they're both Calabi-Yau and they're birational to each other. And they're derived equivalent. So what we're seeing here is some of the examples which led people to make conjectures. So there are these conjectures which are very, very deep and interesting conjectures due to Bondal and Orloff and Kawamata. And the simplest way to say them is basically to do with this arrow here. That if you have two spaces which are birational and Calabi-Yau, then their derived categories should be the same. So if x and y are birational and both are Calabi-Yau, so they both have trivial canonical bundle, then the conjecture is that they're derived equivalent. Right? So the Atiyah flop, or the flop in higher dimensions, is just one example, one tiny little piece of evidence for this conjecture. People have gone a bit better than this. So this is proven in dimension 3. So it's a theorem in dimension. So in dimension 2, it's actually easy. But in dimension 3, it's not easy. And so that was proved by Tom Bridgeland. But in higher dimensions, it is wide open. I mean, wide open. There is no strategy in place for how you're going to prove that. And the converse is false, by the way. There are derived equivalent Calabi-Yau threefolds which are not birational. So it's not the same thing as being birational, but it seems to be closely related. Yeah, if you want to be a little more precise, I stressed that this was supposed to be a local model, right? So if you're doing a flop, it's true that locally the canonical bundle is trivial, But maybe globally the canonical bundles are not trivial. So maybe what you really want to say is not that they're both Calabi-Yau, but that their canonical bundle is locally not changing. Right? And that has a precise definition. It's called K-equivalence. That's Kawamata's terminology. Right? And what if the canonical bundle does change? Right? What if one side is Fano and the other side's general type or whatever? Well, what we saw in our baby example is that then you get a semi-orthogonal decomposition. One space sits inside the other. Right? So I don't think anyone knows how to say this conjecture very precisely, but somehow this is the easy, this is sort of one special case of a conjecture which says something more like whenever you have birational spaces, you expect their derived categories to be related by semi-orthogonal decompositions. Right? Now, if you think about it, it can't be completely straightforward because you could do a birational transformation and the canonical class could get more negative and the category gets bigger, and then you could do a different birational transformation and make the canonical bundle smaller again, larger again, and the category gets smaller, and then how are the two ends related? Right? They both sit inside some bigger space, but how are they related to each other? So it's not clear if you can make a very precise statement at this point. But let me just say that in general, you should expect to see semi-orthogonal decompositions. So this is a very nice, I really like this bit of the story. It's sort of, I mean, birational geometry is so incredibly classical. It's so old, yeah?
I guess I'm just curious about how this isomorphism should come about. In this case, right, you have these windows that you constructed using functions.
Yeah. So am I. Yeah. Yeah. How should it come about? How on earth? Why are they equivalent? How do you construct a? If you can construct a functor between them that has at least a chance of being an equivalence, you're probably almost there, right? That's going to be all the hard work. Yeah.
Maybe it's worth saying that just push and pull by rational rule.
Yeah, that's true. Yeah, if it was obvious how to build the functor, the conjecture would have been proved or disproved by now. It's tough. People are working on it. In theory, I'm working on it. That's what I told my grant committee. What was I saying? Yeah, expect some. Sorry? So in dimension 3, you have a very tight control over what kind of birational transformations can happen, and that's why you can prove the theorem. So somehow you can say all birational transformations are of this form, and in this form, Bridgeland has this beautiful, and Bridgeland, King, and Reed have these very nice description of what happens with flips and how that does what you can think of. Think of the other space. The other big piece of this story, which I'm not talking about at all, is when one space is a moduli space of sheaves on the other, and you have a Fourier-Mackay kernel in the sort of the true sense. And that's the other way you get functors between things. So in the case of flips, you build one space as a moduli space of objects on the first space, and then you use some like universal sheaf to build a Fourier-Mackay kernel, and you use that. It's a very different story from this story. Yeah. What was my point? Yeah, OK. I think that was all the general muttering I was planning to do. OK, so I wanted to point out one special case, which is maybe not so important, but worth making contact with something that I said yesterday. What happens if I set k equals 1? Right? So I'm taking Cn plus 1, and I'm trying to mod out by the action of a C star, which has weights 1, 1, 1, 1, 1, and then minus 1 at the end. OK? Then x plus is just going to be the total space of the line bundle O minus 1 over Pn minus 1. What about x minus? Well, it's the total space of a vector bundle over projective zero space. Right? Projective zero space is a point. If I take the locus y not equal to 0, I cut out the locus where y equals 0, that C-star action is free now. Right? The value of y is basically irrelevant because you can rescale y to 1 with no trouble. And so what you are left with is just affine space of dimension n minus, what? No, dimension n. Dimension n. Right? Which you may as well consider as being in the x variables, right? It's just that the y variable is irrelevant. Okay, and so our Windows technology tells us that you get an embedding of the derived category of affine space into the derived category of the total space of the O-1 bundle on Pn-1. Okay? Now, that's not very impressive because there is an obvious way to get an embedding like so, which is to observe that this guy is the blow-up of this guy in a point. Total space of the O-1 bundle is the blow-up of AN in a point. So there is actually a map between these two guys, which is just, let's call it pi. It's just the blowdown. Right? If you contract the zero section, you're just going to get affine space. That's what's happening. And so there is an obvious way to get a functor from there to there, which is to take a sheaf on affine space and pull it up. Right? And if you mess around with that calculation, it's easy to show it's an embedding. And it's also very easy to show that this functor we just constructed is actually equal to pull up along the blow up. The way to see that is to just ask, what does it do to the structure sheaf? Blow up takes the structure sheaf to the structure sheaf. This window construction, if you stare at it, takes the structure sheaf to the structure sheaf. Right, and that's pretty much it. That's basically the end of the proof. Okay? So I'm probably not going to do it, but I was going to... remember, I mentioned yesterday, right, that the Atiyah flop, the way Bondel and Orlov did it is they pull up and they push down. Right? And we did it with Windows, but actually it's the same functor. And somehow the first step in checking that statement, well, one of the ways to check that statement is to start from this observation that actually this window, in this situation, windows are just the same thing as pull-ups. Right? And push down also come from windows because windows give you the adjoint functor as well. Right? Going the window one way and going the window the other way is adjoint, and pull up and push down are adjoint as well. Right? So if you set up the right problem, then Windows are just giving you back your familiar functors again. Did they tell you the blow-up, the theorem about blow-up and semi-orthogonal decompositions? Yeah? Great. Awesome. So there you go. This is a sort of simple-minded way, in a simple example, to see that theorem about blow-ups giving you semi-orthogonal decompositions. Right? The derived category of this guy has a semi-orthogonal decomposition in terms of the base and something that's left over. You can do all of that. I mean, there's a general theorem, but here you can do it in the simplest example, and you can do everything very explicitly. And if you go through the example sheets, then you will basically work out all of the details. Okay. Right. We should get on to the example that somehow is important to make contact with Nick. Hello. No, the total space of this line bundle is the blow-up. Yeah, if you blow up a vector space in the origin, you get a projective space in the middle as an exceptional divisor, and the rest of the space forms a line bundle over it. That's what it is. Maybe I need some brackets, perhaps. Okay. So let me go back to an example that I talked about on Tuesday. which Nick also mentioned this morning, which is to let C star act on C to the n plus 1 with weights 1, 1, 1, 1, 1, and minus d for some positive integer d. OK? And maybe I'll just try and synchronize notation a little bit. Let me call them x1 up to xn. And the last variable I'll call p, because that's what Nick was calling it. Because that's what Witten calls it, actually. We'll call it p. It was y a minute ago, now it's p. All right? So as Nick said this morning, right, there are two possible choices of quotient. So I will just flesh out a little bit more of what he said. You can take the locus where the x-coordinate's not 0, and you can divide it by C star, and that's exactly what we did on Tuesday, right? And it's the total space of O minus D on Pn minus 1. It's a non-compact variety, similar to what we were looking at over there. And then the more interesting side, which is what I wanted to stare at a little bit more, which we didn't do on Tuesday, right? We somehow didn't spot this when we looked at it on Tuesday, is that we actually have a choice, because instead of deleting x equals 0, I could choose to delete p equals 0. And that is, as Nick said, the orbifold an mod zd. Right? And why is that the case? I mean, Nick was talking as though you all understand this. And I don't know. Do you think they know why this is true? They were? No, I didn't. Oh, is that why? OK. Oh, never mind. I'll explain it to you now, bits of it. This is like that thing in undergrad courses, right, where you have a topic X and then advanced X. And in X, they say, oh, you'll learn all about this in advanced X. And you get to advanced X. And, oh, didn't you learn all of that in basic X? Oh, we don't have time now. Let's plow on. OK, so this is an orbifold, right? Now, what is an orbifold? An orbifold is a kind of stack, right? A simple kind of stack, a Deligne-Mumford stack. What it means is you work on AN, but whenever you do anything, you make sure you're working equivariantly with respect to ZD. Right? Now, we've been doing that all along, right? We have just been working equivariant categories the whole time. So secretly, we've been doing stacks, right? We've been doing the derived categories of stacks. It's much less impressive when you know how to do it, right? It's not difficult. Right, but it is a stack, right? It's a Deligne-Mumford stack. So when I think about sheaves on this guy, I mean ZD equivariant sheaves on AN. And from the categorical point of view, that's all you need to know. You don't need to know this thing as a category fibered in groupoids or whatever you might think it is. What I mean is when I do sheaves, I mean equivariant sheaves. Right? That's all I need to know. So you can view this as a statement about two stacks being equivalent if you like. That's no more sophisticated than the example I set you on the first example sheet, which was saying that Pn is equivalent as a stack to a certain open subset with the action of C star. So if you don't want to say stacks and you just want to be a bit more intuitive, you could say, well, in this example over here, I said the C star action is free. So you can just rescale y to 1, and its value doesn't matter. Right? If you consider the slice, y equals 1, that slices hits all the orbits, 1 to 1. So you can try and do the same thing over here, and it doesn't quite work. So p is not 0, so I can rescale it to 1. I can slice at p equals 1, and that will hit all the orbits. But because the action has weight d on p, there is a residual stabilizer group. Right? The group of d roots of unity acts trivially at the origin in that space. Right? So think of setting p equals 1, then the point is that you have an with a residual action of ZD sitting as the dth roots of unity inside C star, right? Okay. Okay, so now I want to do windows again. For this slightly more confusing example of a birational transformation, right? Something I want to sort of impress on you is that this situation with the x plus and the x minus, it is actually just a birational transformation. And technically, it's no more difficult than the ones we've been doing before. It's just that one side is an orbifold and not a variety. But orbifolds are not things you should be scared of. Most things about orbifolds are actually very easy. So you should really think that x plus and x minus are birational, but one is an orbifold. And another thing you could say while I'm muttering about it is that I told you that x plus, on Tuesday I told you this, x plus is a resolution of a quotient singularity, an mod zd. You remember I said, what's the global ring of functions on x plus? It's some ring of polynomials of certain degrees. It's equal to the invariant ring of this guy. So this is a resolution of singularities. On the other hand, this orbifold is also a resolution of this singularity. If you take that orbifold and say, I don't want it to be an orbifold, I'm just going to take the quotient and get a variety, of course you get this. So this orbifold lives over this variety, and the orbifold is smooth, and the variety is singular, so it's a resolution. So it's the same diagram as in the Atiyah flop. You have two resolutions of the same singularity, and that's connected with how we're comparing the derived categories. Okay, so what do we do with the derived categories? We know that if I take the window to be O up to O(n minus 1 inside the equivariant derived category, we know that this is equivalent to the derived category of x plus. Okay, that was what we did on Tuesday. What about on the orbifold side? What's the window for the orbifold side? And you can probably guess, you should take, just looking at the numbers, you should take the line bundles O up to OD minus 1. So let's argue a little bit more carefully why that works. Okay, so what is a line bundle on this orbifold? Well, line bundles, when we had our quotients by C star, the line bundles just came from representations of C star. So they were governed by integers. Here, a line bundle on this thing will be governed by a representation of Z mod D. And there are only D characters of Z mod D. There aren't infinitely many. There's only D many. So these things are indexed by irreps of ZD. So they go O1 up to OD minus 1. And then, in some sense, you have OD, but it's isomorphic to D, to O again. So OD is, in some sense, trivial, if you want that to exist, right? So you only have this finite list of them to start with. And it doesn't sound very surprising if I tell you that these guys generate the entire derived category. Okay? So if I set W prime to be the window which goes O up to OD minus 1 inside the C star equivariant derived category, then I have a restriction functor to the derived category of the orbifold and the derived category in orbifold just means the equivariant derived category of Cn right? Just take equivariant sheaves and take their derived category, right? So I have a map from this window to here just by restriction, and in this situation, what's obvious is that these guys generate all of this thing. So it's obvious that this functor is essentially surjective. It hits everything, right? So this functor is clearly essentially surjective, which was not so obvious on the other side. So what about it being fully faithful? So I have to check that the HOMs and the X groups don't change. Now, in the C star equivariant derived category, I said sheaves have no cohomology. The global sections functor is exact. So basically, between our line bundles, there were no higher X groups. There was only X0. And when we were worrying about fully faithfulness, the whole problem was, as you restrict the open set, sometimes you acquire higher X groups, right? And that was what we were worried about. Here, the situation is a little bit different, because on this thing, there is no sheaf cohomology either. Taking invariance with respect to ZD in characteristic 0 is also an exact functor, right? So on X minus, there is no higher sheaf cohomology. So if you want to know X to K between OI and OJ, where K is some number bigger than 0, then that's going to be 0. Right? So now there's no problem about X groups suddenly appearing when you restrict, but we lose that problem, we gain a different problem. In previous examples, the open sets were complements of things which had codimension at least 2. So when we went to the open set, the X zeros did not change because we were just going down to some complement of something small. Now we've done something more brutal, which we've cut out a divisor. We've cut out the locus p equals 0, a whole divisor. And so you would expect X zeros suddenly to start changing. Right? H0 is going to change, even if HK doesn't change. So this X0 might be different on X minus and C to the n plus 1. Right, and in fact, if you computed X0 between O and OD, let me say O minus D probably. OD you might get away with. I can't remember. Ha. Yes, no, D. Let me say D. Fine. If I compute X0, so that's just HOMs between O and OD, then I get a different answer if I'm on Cn plus 1 compared to being on X minus. Because OD is trivial on the orbifold, and OD is not trivial on the equivariant version of Cn plus 1. Okay? What changes is that the function P inverse suddenly shows up. Right? So this was something that definitely came up in Nick's lecture, at least in passing, which is that when you're on the orbifold, you have this isomorphism given by, you have this function P inverse, right? No, the other way. Which way? That way. P has degree D, so P has degree minus D, P inverse has degree D, that way. Okay, So that P inverse suddenly shows up when it wasn't there before. So if you're not careful, the functor will not be fully faithful because this x0 changes. On the other hand, I'm using this window with only O up to OD minus 1 in it, so I'm OK. Right? So if you take I and j to lie in the window, which we're going to do, then x0 doesn't change. So the functor is fully faithful. So the restriction functor from W prime to the derived category of x minus, that's an equivalence. So in the end, some of the details are different, but in the end, the story is exactly the same as it was in all the other examples, and the fact that it's an orbifold shouldn't really trouble us. OK, so how can we compare the two sides? I've got my two possible quotients in my pitch, x plus and x minus, and I want to compare their derived categories, so I lift them into windows in the equivariant derived category. And the point is that one of these windows fits inside the other one. W is this guy, W prime is that guy, and depending on your choice of the numbers, one of them sits inside the other. So let's compare these two guys. There are three possible cases. So if n is bigger than k, then window prime sits inside window, W prime sits inside W. So the derived category of the orbifold sits inside the derived category of the space. Quite likely. Where? Where was D? Yes, I do. That's right. When did it become K? It never became K. Just there. Great. Thank you. Oh, was K in the previous example? Yeah, that was why. OK. Of course, it could go the other way around. N could be less than D. W prime could be bigger than W. And then you'd get an embedding going the other way. So the derived category of the space sits inside the derived category of the orbifold. Or maybe the most exciting case is when they're exactly equal, and then the windows are just exactly the same thing. And then you decide that the derived category of, well, let me write it out full. The derived category of the canonical bundle of Pn right, this is x plus. It's the total space of the O minus n bundle, which is the canonical bundle. It's equivalent to the derived category of the orbifold Cn mod Zn. So a space and a very different orbifold have the same derived category. So, OK, this is a bit like the Atiyah flop with the two spaces being different and having the same derived category. But now these two spaces are genuinely different, right? There is no way, that is in no sense is that thing the same thing as that thing, except that they do have the same derived category. Yes, yes it is. From a certain point of view, from a certain historical thread, this is some example or generalization of the Mackay correspondence. The original Mackay correspondence is in dimension 2, and this would be only the AN case of it, and there are D and E cases as well. There are all sorts of higher dimensional generalizations. Right. Yes, and this is also this is also the Calabi-Yau case, right? Before I was stressing the fact that the canonical bundle seems to have some like number associated to it, like whether or not the canonical bundle increases or decreases is the thing that controls which way the embedding of derived categories goes, and it's exactly the same story here. You know, the canonical. It's maybe not so easy to think about what the canonical bundle of an orbifold is, but it does work out the way that the numbers are suggesting. And so it's the direction of the canonical bundle that's controlling this. And in particular here, this is the Calabi-Yau case, right? This guy is a non-compact Calabi-Yau. You've stuck exactly the right line bundle on to cancel the canonical bundle of projective space. So this is a non-compact Calabi-Yau. And this thing, I claim, is a Calabi-Yau orbifold. Right? So the way you think about the canonical bundle of an orbifold is to take the canonical bundle and think of it as an equivariant line bundle. Right? So the canonical bundle of Cn is, of course, trivial. Right? But it's carrying a Zn action. And it might not be trivial for that. In these other cases, it's not trivial. So this thing, but here it is. So this is like an orbifold Calabi-Yau. In other words, Zn acts trivially on the determinant of Cn. Okay, so the Serre, Serre duality doesn't really work on non-compact things, but there are versions of it. And if you look at the Serre functor, it will be a shift. Right? That's the categorical incarnation. And that's equally true here. The Serre functor here will be a shift as well. Oh, I still have 5 minutes left. That's amazing. That never happens. OK. So I should probably give you a little bit of tomorrow's lecture then. So basically what I want to do tomorrow is bring in superpotentials and do this again, but instead of for derived categories, do it for categories of matrix factorizations. Right? And we'll see just how we modify. The same things are true, and I'll give you some of the arguments to fill in why it still works. But instead of starting on that now, let me maybe just give you some general discussion about where this theory goes from here. So I've very deliberately given you the simplest examples where everything can be done very explicitly. But I haven't. The cost of that is I haven't given you really the true story. I've lied to you about how you should define these categories because in the simple examples it works and it's much simpler. So I just want to give you a little hint about how you do it properly. So this window technology turns into a very general story, which was not developed by me, but developed by Halpern Leisner. And Ballard, Favreau, Katsakov. If you're a typography geek, then that's a short dash, and those are long dashes, because these are 3 people, and that's 1 person. But so the general story is that you have, again, a quotient variety, right? So you have a bigger variety y, which for us was just a vector space, and you have an action on it of a reductive group, which for us was just C star. Okay? Y, probably a smooth variety, or you can just about get away with some singular things. Then, using their general theory, you can construct a window. What do I mean by a window? Well, I mean a subcategory inside the G equivariant derived category of Y. Oh, hang on. Sorry, I missed a step. Right. Let me just erase that. The first thing you have to do is make your choices to make a quotient. Right? So we've been cutting things out in a slightly ad hoc way and forming quotients. The way to make it not ad hoc is to learn what geometric invariant theory is, right? So there's a thing called geometric invariant theory, which is fairly old. even by my standards, fairly old, which says that given a particular choices, there exists a nice open set, which is called the semi-stable locus inside Y, such that when you just quotient the open set by G, you get a reasonable thing. It's an open set such that X is a nice variety or orbifold. And everything that we've been doing with our choice of quotients is really GIT, right? But with the examples were so simple, there's no point in explaining the general theory. It's in fact something called VGIT, variation of GIT, because we were doing two different possible quotients. You're varying which choice you make and which quotient you take. Okay? Okay, so you make one of your choices, and you build yourself this nice quotient space, and then there exists a window, so some subcategory inside the equivariant derived category of Y, such that the restriction functor from W to the derived category of the GIT quotient X is an equivalence. Right? Which is exactly what we were doing by our rather elementary methods. So that is just a theorem. Now, what you would like is to do the VGIT, the two different quotients. Right? Somehow the theory became interesting when I said, OK, I have two different quotients, like this variety and this orbifold, and because I can lift them both into windows, I can prove their derived equivalent. Okay? So you would love to be able to say, if I have two different GIT quotients, I can lift them into windows, and then I can prove that they're derived equivalent. Or maybe I can prove there's a semi-orthogonal decomposition, one inside the other. That would be great. That theory doesn't exist, sadly. The theory says you can lift one side to a window, you can lift the other side to a window, and the two windows are so different you have no idea how the two categories relate, right, in general. But there are lots of cases where actually you can compare. So maybe I should write a little bit of that down. So given different quotients, so I have x plus and x minus. We lift them to two different windows, right? And unfortunately, we cannot compare the windows to get any useful information. But in some situations, we can. If the group is abelian, you have a lot more chance. If the space is if Y is a vector space, you have a lot more chance. Basically, the closer you get down to these basic examples, the more likely you are to be able to say something. And the further you go, the harder it gets. So sometimes you have one of them sitting inside the other, or equal to each other or something. But in general, you can't do anything. And maybe, let me just, since I started like 2 minutes late, let me take 1 more minute. I just want to make one comment about how you define these windows, because one aspect of what I've been saying is extremely misleading, and I want to correct that slightly. Let's suppose our group is just C star, and it's acting on some space Y, but I'm not going to assume that Y is just a vector space. I'm going to imagine that Y is some big, complicated, nonlinear thing about which I know nothing at all. But for simplicity, let's assume there's a single fixed point of this action, okay? Like the origin, right? Except it's not a vector space. Okay? Then there are two obvious things you want to consider, which are the locus which flows into this fixed point, the incoming manifold, the stable manifold of it, or the locus which flows out, the unstable manifold. And if you think about all our GIT, all the examples we've done, they're all of this form, right? We had the incoming weights and the outgoing weights. And those were the bits we threw away. And that's how GIT works. This is what you have to throw away. So there are two quotients in this situation. One of them is throw away the purple, and the other one is throw away the red. Okay? So x plus is given by y minus the purple, mod C star, and x minus is given by y minus the red, mod C star. Okay, how do you define the window? Right, that's the bit I wanted to point out. We were saying you take these line bundles and you impose this grade restriction rule. You only take a finite number of line bundles, right? That's a terrible strategy here because I don't know anything about these spaces. I have no hope of proving that x plus is generated by a finite set of line bundles. You will not get Baylinson's theorem, right? It's very, very special for simple things like projective space. This thing is an elliptic curve, right? It is not, then it will not be generated by finite set, right? Okay, it's just not going to work. So you don't want to say, you don't want to take this global perspective where you say, I'm going to take this line bundles and only these line bundles. The trick is to zoom in at what happens at the fixed locus, okay? So what I want to do is take all the objects in the equivariant derived category and restrict them to the point P. Now, what do you get? When you restrict to P, you just get a vector space, except that C star is acting, so it's actually a representation of C star. So it splits into weights. So that's where you impose your grade restriction rule. You say, I want an object such that when I restrict it to P, the C star representations that occur are constrained to lie in a specific window. So this thing only has weights in some specific interval. Right? The specific number that you're allowed is all to do with how many positive and negative weights there are in there, right? Which is some statement about the normal bundle to P and how it decomposes as a C star representation. So this number here is controlled by the tangent space to P. Right, the C star action on the tangent space to P. Okay, and that's your grade restriction rule. So it doesn't say anything about the global nature of your space or your vector bundles or anything. It makes everything local. And then the whole story goes through pretty much the way that I've told you, right? You've seen the key ideas. I mean, there's some fiddling around, but basically that is the point. Okay, yeah, I've overrun. Sorry about that. I will see you tomorrow. I've written you 2 more exercises basically on today's lecture.